Alrighty, we still have some people joining, but let's go ahead and get started. Hi everyone, my name is Amanda DeFelice and I'll be moderating today's webinar. Thank you for joining us on this topic for a technical deep dive and discussion on emergency vehicle detection. This webinar is being recorded and I'll share this with everybody after the fact so that you can watch it again, share it with your colleagues. And a reminder to everybody to use the Q&A and the chat section at the bottom of your screen to submit questions that you have throughout the presentation. So with that, I'm excited to announce our speakers for today. First up, we have Andy Hagan. Andy is the Director of Machine Learning at Sensory, where he spearheads R&D projects to develop innovative speech and sound recognition solutions. Andy holds a PhD in computer science from the University of Colorado at Boulder and has over 2 decades in the field. Andy has worked and studied in both Germany and the US and brings a global perspective to his work. Next up, we have Jeff Rogers. Jeff is the VP of Sales and Marketing at Sensory and has been influential in the development and design of hundreds of products over the last 29 years that use Sensory's speech and computer vision technologies. Jeff has licensed speech and computer vision tech to companies such as Honda, Mazda, Garmin, Panasonic Automotive, Amazon, Google, Samsung, Microsoft, and many more. So with that, Andy and Jeff, thanks for being here today, and I'll hand it over to Jeff.
Thanks, Amanda, and welcome everyone to our EVD webinar. This is going to be a little bit of a different webinar for us. It's going to be way more technical and way less salesy, which is good for me and you who are probably more interested in the technology than the sales side of things. But I did want to kick things off with just a quick overview of Sensory for those that don't know us. I'm guessing most on the webinar have heard of Sensory. We're a well-known name. We've been in business more than 25 years, so we're not new to this game. We've licensed more than our technology has been licensed in more than 3 billion products worldwide. And that goes across all these and more customers that are shown here on the right side of the screen. So you can see a lot of big names there, and some of the names like Amazon and Google and Microsoft and several others have huge speech teams, but they license Sensory because our technologies run entirely on device, are very small and very accurate. And obviously, it's that perfect combination that allows us to do so much with so many different customers and markets. Today, we're definitely going to be focused on automotive and what we're doing there. But as you can see, we play across automotive and IoT, wearable, medical, and many other markets as well. We're mostly PhDs in linguistics and technologists with a light sprinkling of sales and marketing. And we have a broad suite of vehicle technologies. So today, again, we're focused on our EVD, but we also are well known in the automotive space for our wake words, our hot words, our phrase spotted commands, our speech to text, our biometrics. There's a lot that we can do. And if there's a little time at the end of the webinar, I'll show you our latest automotive assistant demonstration that combines wake word, speech to text, automotive language model, a micro language model that handles the NLU, and even an action lookup table and a small language model. So if there's time at the end, I'll show you a quick demo of those things. But again, we can provide a complete SDK, and so everything that Andy's going to be talking about today will have an SDK that we can provide to allow you, the developer, the OEM, the tier one, to do that development yourself. And for speech recognition, we also have our voice hub tool, which is fantastic. It allows for quick development without going out and collecting a bunch of data. And so kind of the combination of these things we can provide. Next slide, please, Amanda. So our automotive solution today is, as I mentioned, it's always on, always available. We don't rely on any network connections. So everything we're going to talk about today can run completely in vehicle. As I mentioned, we provide wake word and wake words today. We're seeing a lot of companies that want to use multiple wake words running at the same time, and Sensory becomes the arbitrator towards, am I talking to this cloud assistant over here, Siri, Google, Amazon, etc., or am I talking to the in-vehicle controls? And so running a single or multiple wake words allows for that. Hot words, again, are software-driven events. So if somebody calls me, I can just say, answer call. I don't have to say, hey, wake word, answer call. Full speech to text. So this provides text for all controls in the car, dictation, so I can dictate text messages and others and do all that in model sizes that range from as small as 30 megabytes to 220 megabytes, which is significantly smaller than pretty much everything else that's out there on the market today. Voice biometrics, this is where we can combine with a wake word with text dependent, or with our speech to text with text independent. So I can say, hey vehicle, and it says, I heard the wake word, and that was Jeff saying it. And when I'm talking and I say, set the temperature for 65 degrees, while I'm saying that, we can be running our text independent verification, say, yeah, I heard Jeff say the wake word, and that was Jeff saying the temperature controls as well. So all that's part of this can be part of our automotive solution. And then we've got automotive language models, micro language models, and small language models. So the automotive language model is basically all things you'd say to the car. It's built in. The micro language model, it basically handles the NLU, or the intents and entities. What was the meaning of what I said? And then we've also developed a small language model where we can basically take something like a user's manual of a car and design that into a small language model, so I don't have to pull out the manual and read from it, or have an internet connection. And then lastly is our emergency vehicle detection, and that's what this webinar is going to be about. So let me turn the microphone over to Andy, and if you've got questions, please ask them as we're going through, and we'll pay attention to those, and at the end we'll do a Q&A. So Andy, off to you, and thanks for joining. A little late your time as well.
Yeah, thanks, Jeff. Thanks for the introduction, Amanda. Yeah, we're talking about EBD systems today. So basically siren detection of ambulances, fire trucks, police cars, and so on. And we build an EBD system that's very accurate. For these kind of systems, you usually need two types of things: technology and data. And we're talking more about the pure tech part, software development and production and testing part, and a little less about data. But data, of course, is also like it's the most important. It's a thing. It's the foundation. You can imagine there are various markets, situations, different background noises, cars at different distances, a police car approaching, leaving, and so on, in China, in Germany, in the US, in any country, and they all sound a little bit different under different conditions, and you need to cover those all. So Sensory has a collection of all that data, self-collected and also scraped from the web, and this is the foundation of everything. And on the next slide, you'll see a high-level view of our solution. You see an optional DSP solution on the left-hand side, and the AP level solution running on the CPU head unit on the right-hand side. The DSP basically, you can run it, it's optional. What it does is filter out 99% of audio whenever there's no siren. It's not as accurate as the AP level solution, but it really helps reduce the power consumption of the head unit solution, because it can take care of the highest percentage of audio and just filter it out whenever there's no siren present. And when there's a little evidence that there could be a siren, it passes it on to the head unit level, and on the AP level, then it's analyzed more critically, and false accepts or something are filtered out. The DSP solution is very efficient, very small, and the head unit level is a little heavier, but I'll talk about this later. On the next slide, you see a little bit of a finer deep dive into the AP level solution. Again, this consists of two stages. A statistical first stage that analyzes the audio very efficiently again, and if it hears a siren, it sends it to a DeepNet revalidation model. And the DeepNet revalidation model basically makes the final call. It says, yes, this is a siren, or no, actually, first stage, you sent me something that is not a siren. It was a good guess, but no. So what actually survives on the right-hand side are actual true siren events. When we talk about accuracy, on the next slide, please, we usually analyze the system with two metrics, and we want to minimize both of them. One is false reject rate, and one is the false alarm rate. The false reject rate is the rate at which we accept, actually at which we kick out actual true events. So imagine you have 200 sirens, real siren events, and you kick out 8 of them. That should not happen. You should accept all the siren events. But you can never be perfect. Some you might miss. The false alarm rate, on the other hand, is when you have audio that does not contain any siren signals. You should not trigger. You should not say, hey, here, I heard a siren. So this needs to be minimized too. And where the two meet, well, you need to minimize both, and then you need to decide on an operating point on the ROC curve and really say, hey, this false alarm rate is acceptable to me. Of course, it would be best if it's 0. It's a little unrealistic. Would be best. But so you have to choose a low false alarm rate and then see that you're good with your false reject rate at that. And that's the optimization task that we're trying to solve. And of course, we need to do this under all circumstances. When we tune to a certain operating point, false accept rate, basically, how many times can we trigger? Do we at the maximum accept a false trigger? And this should, of course, be very low. So what we chose here in our analysis is 1 false alarm in 24 hours of driving time. So when you consider the typical usage of a car, 1 to 2 hours per day, this comes to more than a week, maybe 2 weeks, maybe even a little bit higher. And you during this week or 2 weeks, you accept 1 false alarm per day. We can tune lower. Of course, we can say this might still be too high. We might not be happy with that. Of course, then your false reject rates will also be a little worse. And now on the next slide, you'll see the real numbers here. First stage is a little less interesting because this is the statistical stage only. And that actually runs at a little bit higher false accept rate. The second stage is more interesting. And when you look at the lower right number, the 1.6, that's 1.6%, and that's the false reject rate. So 98.4% of real siren events we detect correctly, and 1.6 we miss. And this is based on a 1.5 second window that's sliding over the audio and moves forward step by step, a few milliseconds forward each time. And this is for a single classification of a 1.5 second context. So when you imagine that you're hearing a 5, 6, 7, 5, 6, 7 second long siren, then you get multiple chances of recognizing that siren. So this is you don't detect it in the 1.5 in the first 1.5 seconds, and you shift forward, you have another chance, you shift forward, you have another chance. Each of those events, you have a chance of 1.6% that you miss it. So in reality, the numbers are probably a little lower the longer the siren goes. You get the point. On the next slide, you see our current models that we have. The numbers you just saw is the sensory small model, the top one here, with 1 million parameters. 1.4 megabyte on disk, so it's a very small but still accurate model. And then we have a little bit even more accurate model, a bigger one, just recently. And it runs at, it has 15 million parameters. Has 17 megabyte on disk. And these are currently the 2 models that we can deploy. What we do is we compare these models to the open source world because we want to know how good we are. We want to know our competition. That's not always easy to get objective numbers there, but you of course can get them from the open source world. And we compare it to the YAMNet 1 million parameter model and the PASST model, which is actually a pretty accurate model out there. It's a big model, 80 million parameters. It's really accurate though. In all fairness, I have to say that those models model more than one sound. We can focus on the siren model. They model more than this one class. Therefore, they have a slight disadvantage here, but they're still pretty accurate. and we will see how much. Um, on the on this slide here, you see our bigger of the two models, and the bigger model is compared to the 80 million parameter model that I just introduced. And you see we're better. How do we do that with 15 million parameters versus 80 million? Well, we have two advantages. Because I don't want to down talk on the PASST model. It's a great model. But we have two advantages for our case that we can exploit. We can solely focus on the Siren model, on the Siren class, and the PASST model is trained on more. And what we can also do is we can train on our own data. We don't test on on the evaluation data, of course. This is a proper experiment. We don't cheat, but we have so much self-collected data in addition that we probably have better coverage, and we probably have better coverage under difficult conditions, I would say. On the next slide, you see the small model that we have. The sensory small model has 1 million parameters, and we compare it to the YAMNet, also 1 million parameters. And here, we're definitely much better. But again, YAMNet models more classes, broader spectrum of classes. So our advantage becomes even more clear here. It's obvious that we're better. But YAMNet is also a good model for the size. It's definitely good. But with our data and the focus on Siren under our conditions, we're beating this. Then I talked about open source now quite a bit. Those models are great, but what the actual tough task, when you did all those evaluations, you trained your model with the usual machine learning toolkits out there, and now you're ready, and now you need to put it into a system, into production. So that's when the real work starts, right? We need to be small and efficient, provide precise timing. We cannot have big delays. And we need to be accurate under special conditions. This can be mostly solved with data work. We need to be deployable on a diverse set of chips, and we need to test well. So talk about low latency on the next slide. We usually trigger when the siren starts within a few hundred milliseconds. And well, the quick response time is essential in the EVD field, right? When the siren starts in your car, you don't want to be informed about it 3 seconds later. You want to respond within. Want to have your system respond within under a second, I would say. And this is what we actually train for and consider. So within the 1.5 second window that we have, where we slide forward, even if the sound appears in there only partially, we recognize it as a siren. If the siren appears partially, maybe 500 milliseconds only, we know there's a siren in there. And this is in the training condition already. This allows us to recognize that very early. Actually, I see 2 questions here. I can probably answer that.
Okay, go ahead, Andy.
So why would the second stage false reject rate be the same at 0 dBA and 20 dBA noise conditions? I assume it would be the best at 0 dBA noise levels. Well, so 0 dBA is when you have as much noise as you have the siren sound. That's equal level. 20 dBA means that actually your siren is stronger than the noise. But at this, when we go back here, yes. So that 0 dBA level is, as said, is harder. Usually it's not as clean as the 20 dBA. But we train for this. So the answer to that question is because we mix noise levels over it. And we actually sacrifice, I would say, some accuracy at the cleaner conditions and to be more accurate at the tougher ones on purpose, because we know under realistic conditions, you hardly ever hear an emergency vehicle under really, really clean conditions. And the other question was, do you have your own separate speech enhancement model, noise reduction and de-reverberation? We can operate with noise reduction. We've done those experiments. It's not as critical for us, but we train on the noise, as I said. So reverb, we train on the different room conditions, so with echoes and all that, room impulse responses. But we actually we consider these sorts of noises and tough data in training. We don't train on clean data. That's how we usually do that. Going back to low latency, and actually on the next slide, we can continue there. The detection characteristics. So when you run our system with low latency and we trigger, what do you get? You get the class information. Why would you need that? You know it's a siren, right? True, in our TSSV SDK that we provide, we also provide other sounds. And potentially, not in the EVD SDK that we specially developed for automotive, but we have the option for other sounds too, like dog barks and baby cries and glass break and these kind of things. And then you would need to know what class triggered. So the class information you get the begin and end time, and you get an event score. The event score is a confidence value, basically. How certain is the system that there really was a siren? And then you can do your own thresholding on top if you wanted. If you have I talked about 1.5 seconds at a time in a sliding window. When you have a very long siren sound, you would trigger multiple times during that siren sound. And what usually happens then is that the begin time of the next event is very close to the end time of the previous one. So if you concatenate these, you get the entire thing. And if the gap becomes too big, then you know it's a really new siren event. That's basically how you go through that. On the next slide, I'm talking a little bit about the systems, the architectures that we cover. For the optional unit, the DSP unit, we targeted the ARM Cortex M series platform, the ESP32, and small chips like that. We have an optimized version with high efficiency for the Hi-Fi 5 DSP. And potentially we can port to many more DSPs. It's just always, if you work in that field, you know, like you need to get the toolkits for that chip, do the compilation process and go through. But we should be able to port to a lot of comparable chips in there. For the head unit AP level system, we support Linux, Windows, macOS, Android, iOS, and they are the usual architectures: x86, ARM, ARM64, and we can usually, if we get the compiler tool chain, we can usually port our system there, because there are no specialties that take us that keep us from porting there. As supported programming languages, so the SDK is developed in C++. So C++, the C++ API comes natural, and then there's Java, Python, Objective-C, Swift, and C#. So these are the usual things that we provide here. Talking more about low memory and power consumption for those small chips and so on. So the DSP solution runs at as low as 5 MIPS. And this is for roughly 50 kilobyte model baked into the DSP solution. With 10 MIPS, you get more higher accuracy, and your model is more like 100 to 150 kilobyte. It might make sense to run a bigger one if you under tough conditions, and 5 MIPS for the very small one. The AP level system runs at about 30 MIPS, and this is the average over realistic conditions long term. So whenever there's a siren, it peaks a little bit more and then goes down again. Our model size is about 1.4 megabyte for the first and second stage combined. And the footprint when you run it is at 4.6 megabyte, roughly. And the
Hey,
next,
Andy, will you take
yeah,
a couple of questions now? We've got a
sure,
few in the chat here. Are the
yeah.
specs discussed today based on external microphone or internal only?
Currently internal only.
Thank you. Suppose I have multiple microphones. Would you also be able to provide distance and direction of arrival of the siren?
Yeah, that's a very interesting question. And so we did experiments. There are two answers to this. So we did some experiments on the internal microphones, and yes, you can estimate direction on a very coarse-grained basis. Left, right, front, back. Yes, with some inaccuracies. You cannot on a 10-degree fine-grained analysis. It's not possible. The theory behind, so we tried that, we measured that, have our beamforming solution, and the reason why it's probably not possible to go down to a finer grain here for the internal microphone is that it's behind windows, and those start vibrating and transmit the sound, and some directionality is lost there. This is what we actually think is happening. So for directionality, we need to go to an outside microphone solution, and we're actually working on that, but this is not available yet.
Thanks, Andy. Okay, maybe one more right now, and then we'll keep going.
Sure.
So last one here. Are you able to discriminate between car horns and sirens, and how so?
Yes, we are. How so? Over data. As our system can learn if a siren is moving with pitch up and down and the car horn is constant. That's basically what the system learns. Similar to a human. I mean, if it's constant, you know it's someone honking. If it's a siren and these kind of patterns, then it's a siren and not a car horn. A steady honk sound is not classified as siren.
Okay, thanks, Andy.
Sure. And then let's talk about software dependencies real quick. Jeff actually mentioned some there that it's basically quite easy. You get an SDK, you get everything baked in, the entire solution. Do we depend on anything? Yes and no. It's transparent for our customers, but internally we use TensorFlow Lite, LiteRT. It's called now LiteRT, formerly known as TensorFlow Lite, and LiteRT Micro for the DSP solution. But you don't have to install or download that separately or anything. It comes with the SDK, and you won't even notice unless you look into the licensing information where we basically disclose that. And LiteRT enables us to use very sophisticated architectures, optimized the latest neural models with attention mechanism and all these things for best performance. And it's tuned for small footprint, especially LiteRT Micro lets us target the smaller chips. And the tech is now ready. We're doing our last tests. We've had sound ID and siren detection for a while, but now we've actually improved our accuracy quite a bit. And we have new models out there that I just talked about. and more data that we collected over the last, well, 1 to 2 years, I would say. And yes, this is fresh baked and ready.
Okay, thanks, Andy. We've got a few more questions coming into the Q&A in the chat here. So I'll start with those. Okay, how does memory and MIPS increase if I want glass break and baby cry in the same model?
Not only one more sound, it probably doubles, but it doesn't scale linearly. If you add more and more, the curve flattens out, especially in terms of footprint. And that's because the statistical first stage does most of the pre-filtering.
Okay.
But yeah, it's definitely doable. It's not a showstopper in terms of MIPS. It doesn't dramatically increase anything or so.
Okay, next question here. What is the biggest advantage of having multiple stages?
So multiple stages, when you do the DSP, it filters out most of the sound. And then you come to the AP level solution, and there you have the statistical first stage, which reduces the workload for the deep net revalidation dramatically. If you didn't have that, you would have to constantly engage the more costly neural network, and this would be as accurate, but it would really come at higher costs, at quite a lot higher costs. So we need the statistical first stage to filter out the obvious non-siren things at very cheap costs, and then we can look at the tough cases.
Makes sense. Okay, have you tested at negative SNR?
Yes, we've tested as negative SNR, and so as you can imagine, the performance starts degrading slightly in terms of false reject rate, because noise becomes stronger and stronger, but we're not bad. You saw the curve up until 0 dBA. Then when you go over this, you're obviously, well, at some point, noise is too much and you won't hear anything anymore. But we do our best to model that in training. So when we train, we don't train with noise and siren equally loud only, but we go beyond that. We have noise overshadow the siren to a certain extent so that we cover for those cases. And the model is able to learn that. Of course, there are limitations to that after a while.
Okay, I've got a couple more here in the chat. Do you always recommend the embedded stage?
No, absolutely not. It helps if you're very sensitive towards the power consumption on the head unit. If you have a lot of things running on the head unit and you really want to be as efficient and only activate the sound ID system there when you need it, reduce MIPS on the head unit, then you can run the optional DSP, and this will help a lot. I mean, it will reduce it by 90% probably, the workload that the AP level has to do, because it filters out most of the stuff. At times, you will get the same MIPS load when there's a siren present. Of course, the DSP recognizes it and sends everything through, and then you have your workload there. But when there's no siren, you're basically idle with the AP level system. So if you're sensitive to MIPS on the AP level head unit side, yes, then I recommend it. Otherwise, you can just run without.
Okay. Next question here. What is the nature of noise that you train under?
It's a lot. So the nature of noise is typical road noise, but then also a lot of noise that happens in cars, engine noise, then all noises that humans make, talking, then music, Music, usually when you run it in a car, you filter out with echo cancellation, or not echo, with channel cancellation. Basically, you know that your radio is playing music. You filter out the music and you get the clean signal. But what if somebody plays music from their smartphone, or some ringing tone comes in, and these kind of things? So we're robust against that. And then, well, everything else that you can imagine. So we collected basically vehicle noise, street noise, all those things, and then we run at different amplitudes, at different noise levels. We overlay that, um, and all that.
Awesome. And Andy, I think you partially answered this next one, but I'll read it anyway in case there's anything you or Jeff want to add.
Sure.
Have you considered highway cases where the noise spectrum and siren spectrum is intertwined and there is energy leakage? How do you filter out cabin noise and music in an internal setup when mixed with cabin noise?
Yeah. So basically, that's what we do, where we subtract the channel of the speaker, where we know that we play music and so on, and then we filter that out, and we get a cleaner signal. If for a specific vehicle, if we know the specific recording conditions, what we can always do is get that set up, play our audio through it, and become even more accurate for a very specific car or setup.
Okay. Let's see here. What is the goal in terms of accuracy you are working towards?
Well, I would say the goal is human-like performance. And when a human can hear it, the system should detect it. You could try to go beyond that. That's a little bit tougher, because you need to know that a siren is sounding from somewhere that you cannot hear as a human, but you know it's there, and maybe the system can catch it. But you kind of need the real evidence, somebody verifying that there's a siren. So uh, our take is that we want to be able to detect the siren when an excellent hearing human can hear it.
Okay. Are your models floating point, and have you checked performance with quantization?
Yes, well, our models are initially floating point, but they're all quantized too. Currently, what we're using 8-bit integers. I know one could go below that. We're currently the models are in date.
Okay. What are the advantages of in-cabin microphones?
Well, the advantages are cost. Most important is cost, because every car, well, every advanced car, modern car has internal microphones, and you can usually just go ahead and use those and add siren detection on top of what other technology is already in there. And then if you have distributed microphones in there, you might get a sense of directionality as well. But costs are the most convincing ones. And for outdoor microphones, it's probably it will probably help a lot with directionality if you get it right. You need to make sure that wind noise and heavier street noise is filtered, or that you become really robust against it. And this is what we're currently also trying to assess how we approach that best.
Thanks, Andy. Okay, you have successfully answered all of the questions currently in the Q&A in the chat. We'll leave that open, so anybody who's still watching, feel free to throw other questions in there as we hand things over to Jeff.
Thank you.
Great. Awesome. Thanks, Andy. And just, I guess one key comment is there is a very large automotive OEM that's designing our Sound ID into vehicles actively. So this is more than just research and demos and SDKs. It's being designed in today. So it's super exciting. Appreciate all the detail on that, Andy. I mentioned that if there's just a couple more minutes, I wanted to share with this group here our automotive assistant model. And basically everything in the dark box there is all part of our automotive assistant. So obviously you have the person that's outside that. They say the wake word. The wake word can be a custom wake word. We're big on custom wake words. Yes, we also support the enhanced Siri and Alexa and others. But we feel pretty strongly about the idea that people should be saying the name of the car or the brand of the car. And again, we can run multiple wake words at the same time. So I could say Siri and go off to Siri, or I could say, custom wake word to do things in the car. Then next is our acoustic model. And again, that's the language that I'm speaking. After that, it goes to our language model, which is all things designed for that you would say to the car. And so as an example, how far can I drive without refueling? The NLU, or the micro language model, then takes over and says, okay, what was the intent entity of what I said? They're asking about the distance available. And then the action lookup table provides that output as far in terms of an engineering kind of table where I can say, oh, okay, this is the question that's being asked, provide this information or do this feature here. So if I can grab the screen here from Amanda, I've got our demo running here. And what you're seeing is this is all running on an Android tablet. And you can see that we support a whole bunch of different languages here, more than 35. I'll just stick with the English for this one. The domain is automotive. We support a variety of models, different domains, TV, hospitality, IoT, wearable. And then under the model size, there's different sizes that we support. So right now I'm using our 227 megabyte, which is really, really small compared to most solutions that are out there. But you can see that we've got one that's 50 megabytes, another that's 91 megabytes. And we got a couple larger ones that include a small language model. That's the SLM in there, 1.7 gig and 1.8 gig. But the idea is that we can design to the ability of the hardware in the car. So a low-end car with a just radio control, as an example, yeah, maybe we just use our 50 megabyte. But keep in mind that all these numbers include everything that I just said on that last screen. So it's the acoustic model, the language model, the micro language model, the action lookup table. So there's a lot packed in there. So it gives me some examples, and I can basically just say anything that I would say to the car. So I can say, Voice Genie, open the sunroof.
Opening the sunroof.
And so here's what I say, and then you can see over here, it's saying this is the system action lookup table. So it knows, okay, go and do that. Voice Genie, roll down the front windows.
Opening the front windows.
And with the automotive language model, you can say things like, Voice Genie, crack the front windows.
Opening the front windows.
So obviously that doesn't mean break the window or crack it. It means open it. But, again, we've designed it so that people can speak naturally. You don't have to memorize grammars and things. Things like, Voice Genie, turn on the front windshield wipers.
Turning on front wipers.
Or I can say things like, Voice Genie, switch on the wipers.
Turning on wipers.
So whether I said turn on the front windshield wipers or switch on the wipers, or I could do the rear wipers and it will recognize that as well. Voice Genie, set temperature to 67 degrees.
Setting temperature to 67.
So again, just anything that I would say to the car, I can say to this voice assistant. Voice Genie, dial 408-898-7671.
Dialing 408-898-7671.
And I ran through that really, really quickly, obviously. Or things like, Voice Genie, turn the radio and listen to 106.5.
Tuning radio to 106.5.
So the other thing that we've done is that we've gotten really smart with wake words. And here's an example where if I go into my settings here and I change to, instead of always have a wake word listen, you have a wake word run after leading silence timeout. So this makes it really smart for us. So if there's a series of things that you might want to do one after the other, you don't have to wake word, say the thing, wake word, say the thing. So I can, as an example, I'm driving along and I want to cool off the car. I can say, Voice Genie, open the sunroof.
Opening the sunroof.
And roll down the front windows.
Opening the front windows.
Set the temperature to 68 degrees.
Setting temperature to 68.
and turn off the front seat warmers.
Turning off front seat warmers.
So by going through that, I could say command, 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 command after the wake word. And then there's a slide or a knob where I can adjust how much time do I want for that trailing silence. And I've got it set at like 1.2 seconds. So if I say something like, voice genie, call home.
Calling home.
Okay, that was really cool. And I'm talking right now, and you can see that it's recognizing everything that I'm saying. So this is a great demonstration of our speech to text, but this is not what I want the car to listen to. And so you can see nothing happens. It ignores it. It says, okay, yeah, that's not meant for me, do nothing. And all of this, again, is running on device. I don't have to go to the cloud for any of this. And so as you look at that speech to text, that's pretty awesome. So one more quick demo here. If I go to our small language model, and again, as I mentioned at the opening, we took a Honda Accord user's manual and built out a model that includes that. And basically, the approach we're using uses kind of a common approach such as quantization, RAG, parameter efficient fine-tuning, RLHF type post-processing, prompt engineering with longer context windows, and proprietary in-house knowledge for what works best to reduce size and reduce hallucinations. Because anytime you have an LLM, obviously there can be hallucinations. So we're trying to keep it more specific to things that say the car. So if I say things like, voice genie, it's too hot in here.
Lowering temperature.
Voice genie, roll down the rear windows.
Opening the rear windows.
So again, that's coming from the system action lookup table. Or voice genie, what kind of oil should I put in this car?
You should use Honda Genuine 0W20 engine oil with a viscosity of 0W20.
So that's all coming from the user's manual that was designed into that SLM. And so other things like how do I change the wipers or how do I program my garage door, anything that you would go to the manual for, rather than pulling the manual out of the trunk, or sorry, out of the glove box, or trying to connect online, you can just now ask the car, and that's all been built in. So you saw kind of two different things that happen there. The system lookup table, which is all part of that automotive language model that's really, really tiny. And then this small language model that's 1.7 gig, which again includes the acoustic model, the automotive language model, the micro language model, the action lookup table, and again the small language model. So with these types of sizes, we can totally run on device in the car, and all this is running on a CPU, not running on power hungry and expensive GPUs or more expensive types of hardware. So again, running in low to mid-end vehicles or high-end vehicles, all that's supported with our automotive assistant.
Hey, Jeff, we've got a couple of questions here in the chat about this demo, so I'll lump a couple of these together.
Okay.
So they say here, for windows, can you specify an amount to raise or lower the window? And similarly, for the wipers, can the speed be specified?
Absolutely. Yeah, so I could say turn on the wipers. I can say run the wipers intermittently. I can say run the wipers at 50%. That's all built into the language model. Good question on the windows. I've never tried that. Voice Genie, lower the windows 50%.
Opening the windows 50%.
The answer is yes, already built in. Great question, whoever asked that one. Thank you.
Great answer, Jeff. All right, we'll give folks just another minute here to put in any last minute questions or answers. So I'm keeping an eye on that. Jeff, Andy, anything we missed? Any last minute topics here you want to cover?
I'm good from my side unless there are no
Good.
questions.
All right.
No, no, thanks
Jeff
so much.
and Andy.
Yeah, no, we're excited to provide a complete automotive solution. And this webinar again was really focused on the EVD and our Sound ID. But as you can see from my quick last minute demos there's a lot more that we can provide as well. Thank you.
Awesome. Thank you both. And everybody, thank you for attending. I'll send out a recording here in the next day or so. Thank you all. Bye-bye.
Thank you. Bye-bye.